Hello, I welcome you all to my third lecture in this lecture series. Today I will be mostly talking about the mechanical properties of structural steel. So, the most important mechanical properties of structural steel from the point of view of a structural designer are yield strength, ultimate strength or tensile strength, ductility, toughness and fatigue strength. The first two properties of structural steel, that is yield strength and tensile strength, have already been discussed in the previous lecture. So in this very lecture we will talk about ductility, toughness and fatigue strength. So let us start with ductility. Ductility is the most desirable property of structural steel. It is defined as the ability of a material or a structure to undergo large inelastic deformations before failure. So in a sense, the ductility indicates the extent to which a material or a structure can deform beyond the limit of yield deformation before failure. In other words, the amount of permanent strain, that is the strain exceeding the elastic strain up to the point of fracture, is a measure of ductility. That is, this portion is the measure of the ductility. That is, this is the yield strain and this is the strain at the fracture point. So strain from this point up to this point is actually the measure of ductility. Mostly the ductility of steel is measured by determining the percentage elongation of the test specimen or the specified gauge length. And the specified gauge length is given in IS 2062-2011 is L equal to 5.65 under root of S0, where S0 is the cross-sectional area of the specimen and the percentage elongation, which is actually a measure of the ductility, is given by, that is, percentage elongation is given by elongated length minus gauge length divided by original gauge length multiplied by 100. For example, we have a specimen whose gauge length is equal to 200 mm and the elongated length of the specimen after the test has been performed on it is 240 mm. In this case, the percentage elongation, which will be a measure of ductility of the material, will be equal to elongated length minus gauge length over original gauge length multiplied by 100, and that will give you 20. That is, the percentage elongation in this case is 20. The minimum required percentages of elongation for various grades of steel are given in table 2 of IS 2062-2011. So as you can see, table 2, mechanical properties of structural steel, clause 5, we have different grades, that is E250, E275, E300 up to E650. And the tensile strength for this grade, that is E250, is 410, and the yield stress for grade E250 is 250 Newton per millimeter square when the thickness of the member or the specimen is less than 20 mm. And when the thickness of the member is between 20 to 40 mm, the yield stress is 240 Newton per millimeter square. When the thickness of the member or the specimen is more than 40 mm, the yield stress is taken as 230 Newton per millimeter square. Similarly, for other grades of steel, we have the tensile strengths as well as the yield stresses for different thicknesses given. And the percentage elongation at a specified gauge length is given by, for example, for E250 grade we have minimum percentage elongation is 23, and for E275 the minimum percentage elongation is 22. Similarly, for different grades you have the minimum percentage elongations given in IS 2062. Thus, the behavior of building materials under loads can broadly be classified into two categories: brittle and ductile. The two categories can be distinguished by comparing the stress strain curves. The ductile materials exhibit large plastic strains and yielding before they fail. On the other hand, brittle materials fail suddenly and without any warning. Thus, ductile materials such as steel are a natural choice for structural members in buildings or any other structures, because considerable warning is desirable before a structure fails. It is observed from the stress strain curves that ductile materials are capable of absorbing much larger quantities of energy before failure. As you can see from the stress strain diagram, we have two materials, that is brittle material and ductile material. In case of ductile material, large plastic deformation occur before failure, whereas in case of brittle material, no plastic deformation occurs and the failure is sudden. So in brittle fracture, small deformations occur, no plastic deformations occur, no necking is observed, and when we observe the surface of the broken specimen after the tensile test has been conducted, we observe the two surfaces, broken surfaces rather, are flat. Whereas in case of ductile failure, there are large plastic deformations, there is necking as well, and there is cup and cone shaped failure surfaces obtained in this ductile failure. Now we have another important property of structural steel, that is toughness. In structural steel design, toughness is a measure of the ability of steel to resist fracture or to absorb energy. According to Roffey, material toughness is defined as the resistance to unstable crack propagation in the presence of a notch. So, for uniaxial tension, toughness can be expressed as the total area under the stress strain curve up to the fracture point, that is the point where the curve terminates. So this area, whole area, will give you the modulus of toughness or simply toughness for this material. But since uniaxial tension rarely exists in real structures, particularly in the region of connections. So a more useful index of toughness is based on the more complex stress condition, or probably the triaxial stress condition at the root of a notch, and this is called notch toughness. Notch toughness is the measure of the resistance of a metal to the development and propagation of a crack at the base of a standard notch, commonly using the Chorpy V-notch test. So this test uses a small rectangular simply supported beam having a V-notch at mid-length. The specimen is fractured by a blow from a swinging pendulum, and the amount of energy absorbed is calculated from the height up to which the pendulum rises after breaking the specimen. And the amount of energy absorbed will increase with increasing the temperature at which the test is conducted. So the more ductile the steel is, the greater will be its toughness. On the other hand, the lower its temperature, the higher will be its brittleness. So as you can see in the figure, is shown a standard specimen for Chorpy V-notch test. We have another important property, that is fatigue. In the case of structures subjected to a very large number of cycles of fluctuating stresses or fluctuating loads, typically at least 100,000 load applications, failure may occur by the continued growth of micro cracks in the material at stresses which are well below the stresses necessary to cause ordinary static yielding or collapse. Such a behavior is termed as fatigue. Most civil engineering structures do not experience loads approaching their design loads very frequently. Of course, there are certain exceptions, for example in crane girders, in railway bridges and offshore structures subject to wave loading. When it is realized that 100,000 cycles correspond to 10 applications of, approximately 10 applications a day for more than 25 years, it becomes clear that fatigue is unlikely to be a problem for ordinary building structures. It is more significant in the case of bridges. So members repeatedly loaded, primarily in tension, are more susceptible to developing fatigue creaks. The behavior of steel in fatigue is measured in terms of the stress range and the number of cycles of loading and unloading. And the stress range is denoted by S, whereas the number of cycles of loading and unloading is denoted by N, and the resulting a curve represents SN curve. So the stress range is the difference between the maximum and the minimum stresses in a member or connection during one load cycle. So the greater the number of cycles of loading and unloading, the smaller the allowable stress range that a structure or the connection can resist. The fatigue strength of a steel structure is usually determined at service load levels. It is a function of stress category, which in turn is greatly dependent on the connection details used in the structure. It is also a function of the stress range in the member. The stress range is usually higher when the steel members and the connections are subjected to stress reversals For example, tension in one cycle and compression in another cycle due to live loads. So when a member or a connection is subjected to only compressive stresses, fatigue risks cannot propagate. So fatigue doesn't need to be considered for such members which are under compressive forces. The lower the stress range, the higher the fatigue strength of the member or connection. So fatigue is a major consideration in the design of steel bridges and industrial crane girders, where the maximum number of live load cycles may exceed 2 million cycles of loading and unloading throughout the life of the structure. So such structures as well as structural elements have to be checked for fatigue. Some other relevant properties of structural steel are modulus of elasticity, shear modulus, Poisson ratio, coefficient of thermal expansion, and unit weight of steel. This unit weight of steel is generally taken as irrespective of the grade of the steel, or rho or gamma is taken as 78.50 kilonewton per meter cube, or is taken as 7850 kg per meter cube. And the coefficient of thermal expansion alpha, it is taken as 12 into 10 raised to power minus 6 per degree Celsius. And the Poisson ratio mu is taken as 0.30 for structural steel. And the modulus of rigidity or shear modulus is taken as 0.769 multiplied by 10 raised to power 5 Newton per millimeter square. And the modulus of elasticity of steel, irrespective of the grade of the steel, is taken as 2 into 10 raised to power 5 Newton per millimeter square. So this was all in today's lecture. Thank you.